Okay, so let me switch in English. So we are starting our session on computational digital humanities, or just maybe digital humanities as usual term for applying computer science in different application domains in humanitarian science, in application of NLP, and so on. And we have first presenter for today's session. The title of the topic is Automated Search and Analysis of Rhythmic Features in Prose of 19th to 21st centuries. And we have presenter, Ksenia Лагутина. So as soon as you are ready to share, please start your talk.
Yeah, but please enable screen sharing.
Yeah, could you try right now?
Yes, thank you very much. Can you see my screen?
Yes, could we go to full screen mode, possibly pressing Ctrl+L or something like this? Yeah, now we see it and you may start.
Great, thank you. My name is Ksenia Лагутина. I present the paper Automated Search and Analysis of Rhythmic Features in Prose on the 19th-21st centuries. What about background of my work? We study linguistic features, especially rhythmic features, and linguistic features are usually applied as a part of complex text model in text processing tasks, but we are almost do not investigate it separately, and we are unfortunately quite rare in state of art, especially rhythmic features that have different definitions, different applications, so we are almost not studied, but we can be relevant indicators of the complexity of a text, of mentionability of a text, and we can be good markers of the originality of a paper, of a style of the time period, and so on. That's why we decided to compare the style of particular centuries, of 3 centuries, 19th, 20th, and 21st, and decades in these centuries, and visualize the rhythm statistic and see the difference in rhythm of different centuries. We chose rhythm figures that are good markers in the typical prose. There are lexical figures, anaphora, diacopa, eponylipsis, epiphora, and so on. For example, anaphora is the repeating words in the beginning of the sentences. Diacopa is the repeating words in the middle of a sentence, and so on. So we use figures that are based on repetition of words or phrases or different grammatical constructions, like epithesis, repeating interrogative sentences, and so on. We use the prose rhyme detector instrument to extract these figures, and its search quality reached 1895% for different figures. When we experiment with figures, first of all, we revert these figures into statistical elements. In the next slide, I describe the statistic of these figures. So we search rhyme figures, when we compute statistical features, and when we visualize with statistics and test with statistic in classification by centuries. For visualization, we compute how many times figures figures appears in the text, and divide the number of each figure up to the number of sentences and then multiply by 100 sentences. So we have the average number of figures per 100 sentences and average number of different of each separate figure per 100 sentences. And also we compute the percentage of figures among all figures. And for classification, we take the number of figures per one sentence, so we don't multiply by 100. And also we compute features that describe the structure of figures. Also, we compute the structure of unique words with words that repeat only once in rhyme figures, and we compute fractions of nouns, verbs, adverbs, and adjectives among all the words that in rhyme figures appear in rhyme figures. After all, we visualize these features as box plots and plots. For classification, we use bidirectional LSTM, a neural network with a LSTM layer. And also on the slide, we have a link to the PROS rhyme detector, the tool in which we realize figure search, feature computation, classification, and visualization. We use for experiments we found four different languages: English, Russian, French, and Spanish. We use literature, novels of the 19th, 21st century, about 20 texts per decade. We have chosen. Also, corpora has from 30 to 40, 20 text, from 340 texts to 420 texts. Also from 19th century to 2019, yeah. And also we divide. From corpora we extract from each text. We extract the fragments of the same size of about 50,000 characters, including spaces, letters, punctuation marks, and so on. So here we can see the visualization of English language rhyme. On the left you can see the box plot. On the x-axis you can see the number of figures per one sentence. And on the y-axis you can see the decades. So we can see in the 19th century there are more lexicogrammatical features than in our centuries, and the plot confirms with statistics. We can see the number of figures per 100 sentences of all lexicogrammatical features, and the plots for most popular lexicogrammatical features, diacob and polysyndeton. So diacob is the most popular feature. It reached up to 80 figures per 100 sentence in 19th century, and during the 20th century it lost in number, and in the 21st century it remains very close to the end of the 20th century. So in the box plot we can see that we can see the range of these features from minimum to maximum. So we can see in the 19th century the range is the maximal, and in the last years where this range is minimal. So the authors really use rhythm features, and they have almost the same number of features per 100 sentences. And for Russian language problem, we can see the close trends. So we can see that the number of features decreases during the decades, but in the end of 19th century and the beginning on the 20th century, you can see the maximum of rhythm features, and also the number of figures per 100 sentences is lower than for English language. After all, we use these features to classify text by 3 centuries, 19th, 20th, and 21st, and we see quite good results for English and Spanish languages, where F measure exceeds 80%, but for Russian and French results are quite low. They are less than 70% of F measure. So rhythm features separately, so quite good classification for English and Spanish, and for Russian and French we need to use another statistical features to classify texts by centuries better. So rhythm features are relevant stylometric markers of the text for the problems of computational linguistics. So we can see that after all, we can, for all 4 languages, can describe some tendencies in rhythm statistic during decades. So this sort of statistical analysis of rhythm allow for classical linguistic experts to perform expert analysis at a higher level of generalization, because they can find rhythm figures automatically, and so see the picture of rhythm figures in a text in a whole, or using this statistic. Also, we compare texts and even decades for the large number. So we can perform experiments for a large number of texts. Well, among all rhythm figures, the most frequent features are Jacob and polysyndeton. The third is anaphora. All another features are quite rare in the text, or will appear only once or twice per 100 sentences. Well, that's all what I want to say. I'm ready to answer to your questions.
Okay, thank you very much for your presentation. So we don't have too much participants in Zoom, so maybe let me ask 2 questions that I'm interested in. So first of all, do you expect some domain shift between the languages to affect your model? So for example, you have something like Japanese poems such as Hokku, in which you have, different type of rhythm compared, for example, to Russian or English or in general European languages. That is my first question. And the second question is it possible to apply apply this kind of models, or I mean some findings from your model for example, generating poems in a given style or given rhythm?
Thank you for your questions. What about first about languages? Well, we experiment only with with Roman languages, Indo-European languages. So we are we have the same definition of rhythm figures. So we can use this model for them. I think for Japanese, for Chinese languages, we should use another definitions of, I suppose, for rhythm figures and another ways of text processing even. But for all Indo-European languages, I think this model fit quite good. And the second question, could you please repeat the main?
Yeah, so could your model be used, for example, for generating poems in a given rhythm?
For generating, well, yes, we can. For some part of generating, I think, yes, we can model text rhythm of yes, we can actually use it for some kind of prose texts and apply some rhythm figures in text generation. But well, they may be quite outdating text, because in most cases this text rhythm is used in 19th century or the first in the first half of the 20th century, but now authors prefer to use other rhythm figures, and these figures are it's the future direction to model a rhythm of modern authors.
Okay, and how do you think, what's the difference between the presented languages? So maybe, I mean, just from your point of view, so what are the main findings from the difference between, for example, Russian languages and other European languages? So what differs Russian language from the written in poems compared to European languages?
Oh, yes, well, Russian languages. I should say I'm not a linguist, so my my conclusions are quite well. Well, my conclusions are not very deep. I see from the point of view of computer linguists. Well, I see that in Russian languages, the length of the sentences, in average, is bigger, and Russian language authors rarely use rhythm features. They actually prefer not to repeat words or they prefer to use synonyms. Also, that's the main difference between Russian languages and our European.
Okay, thank you very much for the presentation. It was a brilliant talk. I can see it's new insights. I mean, where you could analyze poems by natural language processing and general machine learning techniques, and that's quite useful. Again, thank you for your presentation.
Thank you very much.
Okay, so I will be bothering with two talks from my side as not a session chair, but mostly as authors of next two papers. So let me share my screen. And the first talk together with Marina Mitrofanova is about leveraging linguistic features from graph-based text representation for language clustering. So basically, let me dive directly into details. So it's like this work is devoted to the problem of clustering languages from small text by using graph embeddings and measuring linguistic proximity of languages. So basically, some languages are more close to another based from linguistic features. And our idea was to compare and apply different approaches based on one layer or multi-layer linguistic network embeddings, which basically represent text as a multi-layer networks. We present just initial results on the topic and supervised language representation models via graph embeddings, text embeddings as a general direction of further studies. Basically, if we just want to visualize sorry, it's the wrong typo with the header. So if we want to visualize the family of languages, so we have a number of languages, and some of them are more close to each other than others. So, for example, you have Indo-European group, in which you have Indo-Iranian and Balto-Slavic groups, and so on. And basically, the question is how you could analyze the closeness of these languages just based on the data. And the answer will be the following thing. So we have some text, and we could extract large corpus for each of these languages. For example, taking Wikipedia written in these languages. And then we could build different layers representation based on different linguistic networks. So the first and the simplest one is just using backgrounds, construct word co-occurrence networks, in which nodes are tokens or lemmas which are connected if one follows the other directly in the sentence. Also, you have syllabic networks, which is basically a predefined list of syllables constructed with similar word co-occurrence, but only with a predefined list of nodes. Morphological networks, which nodes are basically morphological units and connections are their relations. We also have syntactic networks in which the nodes are words and the edges are grammatical relations between them. And semantic, where the nodes are words and they are connected if they share some meaning across them. And basically, you could construct again different network representation of the same text. Our idea was the following: so it's like for the same language, you could construct different multi-layer networks representing different semantic or syntactic or in general any kind of linguistic dependencies between words, and then merge the words across the layers and consider this kind of representation. This kind of representation as meaningful features without any kind of supervision for finding similarities or constructing embedding of languages and then understanding how to cluster them. Basically, our data sets contains non-parallel text from Wikipedia dumps. In total, we have over 100,000 texts for 20 languages in 8 language families that were presented in the diagram before. The length of the text doesn't exceed 20 and not less than 10 sentences. So basically, we consider just very small text. So that's the basic idea how it should be done. And the test to test the performance of the model on new incoming text and languages, the data set was split into train and test sets in proportion to 75% for train set and 25% for test set. And all unseen languages represent a member of a family from the training set in order to see if the new common languages are clustered together with another present member of the language family. So basically, we don't generalize across new families of languages, but just try to understand whether new languages fit to the current family, so we already know the number of clusters. For evaluation of clustering techniques, when we have some supervision, I mean, we know ground truth values, we use several metrics such as adjusted friend index, normalized mutual information, and adjusted mutual information. So basically, all of them. So if you just consider the basic definition of friend index, it may be something like explaining similar to accuracy in the classification tasks. So normalized mutual information, you just understand how the joint distribution of two clustering assignments is comparable to independent distribution of each clusters, and you have some normalization procedure. And again, adjusted mutual information is quite similar with adenine, another variant of normalization. And if we go into details about how we do clustering, we suggested to use hierarchical clustering approach based on varus linkage with Euclidean distance is used for received multi-layer graph embeddings without any prior linguistic knowledge. Only the assumption that some languages are related to each other and that there exists some sort of hierarchical evolutionary relationship with them. And the distance between clusters is defined as the difference of intercluster parameter after combining two clusters compared to keeping them separately. So basically, if you have two clusters, you could unify them in one cluster and compute the average distance between its centroid to all the other elements inside the cluster. And it will be the norm for unified cluster, and you need to subtract similar norms for each of these clusters. So basically, we obtain some qualitative results that allow us to compare different representation of text, one-layer and multi-layer networks. And as you could see that, for example, one-layer networks such as word co-occurrence, they don't show good performance just based on array metrics. And multi-layer networks show some better performance, but of course, text-based methods shows the best results in all the cases. And when we see inference on seen languages and inference on unseen languages for the new text, we see that many metrics just drop significantly, and especially for unseen languages, we don't generalize at all for all the methods. But for the text that we already have seen, we at least have some inspirations that our methods may work out. So despite significant drop in the adjusted strength index, we still match the existing clusters. If we discuss the comparison of visual comparison of graph and text embeddings via UMAP projection, you see that in the graph methods, you have very strong mixture of all the clusters. And of course, we could highlight some general clusters. So, for example, Japanese languages and Turkish languages were two families of languages were separated very good. But for example, compared to text embeddings, of course, we have much better results regarding to separation of this text. And it's also some kind of understanding that graph embeddings may work out, but right now it's like we need some more novel and maybe more advanced models to proceed further with this kind of methods. And as a conclusion, again, the results have shown that in the case of absence of the information on specific units of language with only one structure of coherence preserved, the text-based approach proves to be superior to graph-based methods, in the contrary to our assumption. Further study for graph embedding-based approaches is required. So that's the end of my first presentation, and I will be glad if you will ask any questions regarding this talk.
Yes, thank you very much. And I want to ask about your text model. How good is it in interpretation by classical linguists and so on?
Yeah, I mean, so basically the original data were hardly interpreted by linguists, and this family languages as ground truth is well known and abides all the linguistic knowledge that we have. Regarding our model, I mean, the problem is the following: so that when you construct graph embedding in a unsupervised manner, it's not an interpretable model. But when you assign the final cluster, you could just say how well your clusters overlap with ground truth. So in this case, we could say that for the trained sets, we could somehow generalize and it fits more or less to the ground truth. But for unseen languages, our model does not generalize well. And we need some more study for understanding how well it should work out for example, for methods that do not take any kind of linguistic information, just works on text representation by graphs. So we still don't have some good results to say that we could omit linguistic features at all.
Okay, thank you.
Okay, thank you very much. And let me go. So we need to start the third talk, and again, it will be presented by me. So it's another work about Russian language in particular, which is done in conjunction with Vera Davıdova and Olga Gerasimova. So the work title is Context-Dependent Word Embeddings for Word Sense Induction for Russian Language. It's a long talk, a long title at least. In the present work, we aim to use context word embedding, such as using Elmo BERT models applied to word sense induction for Russian language. Basically, the main idea is the following: that we have some words that have different meanings, but their written form is the same. And in word sense induction, you need to guess the type of sense you mean by this word without any kind of supervision. So basically, we need to apply clustering to understand what is the meaning of the current word. And since embeddings produced by these models depend on the context, we presume that they could be able to capture the particular word meaning used in particular sentence. We created a word sense induction system for Russian languages based on clustering context-dependent word embeddings constructed by pre-trained language models. So here, just me let you introduce some examples of these ambiguous words and their embeddings. Yeah, so for example, we have the word bore, and bore may be chemical element. It will be it may be Serebriny bor, which is kind of park or forest. We have pine forest and some other senses that may be abused. For the word look in Russian, we have interpretation as an onion, so it's kind of vegetables. We have another cluster, for example, which is represented by bow, so from which you could show the arrows. And the same goes for sreda, which has much more meaning. So you have sreda as environment, sreda as Wednesday day, and so on. And of course, we don't only have this kind of ambiguous words for just normalized and tokenized words, but also, for example, if we consider the word banka, then banka in this case may be bank as means some storage object in which you could play something, and it may be just a version of the word bank, which is basically finance organization. And for example, I have a call from bank in Russian. It will be again the same. Мне позвонили из банка, and this kind of words. Of course, make the text embeddings and word embeddings noisy, because different senses imbue different embeddings of these words, and you need to properly separate these senses between one and another. And just looking at the projection, you already understand that it's like by different contexts. So basically, use these words in different sentences, you'll have different embeddings of this context and these words in particular. So it's like you have different approaches to work on. In our case, we work on 3 models, which are straightforward implementation of context embedding. So the first one, which is called average send, it's basically a weighted average of context sentence embeddings for each context that we used. So by sentence embedding, we use just a fixed mean pooling of all contextualized word presentation from 3-layer LSTM model output from Elmo or BERT model. Average send no target is basically the same model, but dropping the target word embeddings. So basically, if we have ambiguous word, let's drop its embedding, and that was the second model. And the third model is about target words. So basically, word representation of target words are the weighted sum of 3 layers again of Elmo LSTMs, where the weights are trainable. So in this case, we allow to train the weights to consider proper target word representations. While context word embeddings differ for the same word occurred in various contexts, clustering of such words embedding can be able to induce meaning clusters. So basically, the idea is the following. So the word embedding in the context embeddings is defined by the context. So basically, we already understand that if we have the word zamok or zamok, we'll have different meanings, whether it is castle or it is locking mechanism, because we'll say we are opening, and it should be a locking mechanism. And we are entering, then probably it will be a castle. And if I say, for example, we are viewing, then it may be both. So, for example, you may be viewing locking mechanism if you lost the key, and you may be viewing a castle as a sightseeing object. So in this case, we also understand that there is ambiguity even in the use of the context, but we try to apply clustering to just try to separate these meanings in unsupervised manner. In our cases, we have 3 data sets, and basically all those data sets were part of RUSET 2018 competition for word sense induction and word sense disambiguation for Russian language. So in the wiki data set, you have very small number of words with just 2 or 3 number of senses. Then we have also Russian National Corpus, in which we have much larger number of ambiguous words, and in active dictionary we have the largest number of words and multiple senses used, and much more number of contexts compared to the first data sets. So again, for clustering metrics, so first of all, we just say that we don't know the exact number of meanings. So in this case, we use affinity propagation plus grid search to determine the number of classes. And finally, we usually use just k-means for final clustering. For word sense reduction, we also tested that agglomerative clustering works well, and we also tested the hierarchical DB-scarn algorithm. And for the final metrics, we again use adjusted random index as a classic metric, which is used when we know ground truth, which was reported in the competition. So the final pipeline of processing the word is the following. So if you have ambiguous words and its context, you remove the target word, then preprocess it for elm and BERT context embeddings, vectorize their context, create context embeddings and target token embedding abstraction, and then just cluster. So as you see from all the comparison, we have 3 models and 2 possible context embeddings based on ELMA and BERT models. And as you see, the best results were achieved by target word BERT model. So basically, let's cluster target word in the BERT representation. It achieves the highest results in our cases. As for qualitative analysis, we have different results. So, for example, we have the best results, for example, for the word douche. And again, douche, it may be bathroom, douche, it may be something like souls, and so on. And we have around 80 contexts, and it was clustered ideally. Then we have some much more complex examples, such as Belka or Belka. So basically, whether you are using protein when you're saying Belka, for example, or you're using Belka as a squirrel, as an animal. And I mean, I'm not sure why it was hard to cluster, because context should be different, but maybe, I mean, some animal domain which might be related to large corpora with regard to biology and with regard to animals, so they may be intersected. So it may be the point why our work doesn't work even in such simple scenario quite well. And finally, if we want to compare our analysis to the words that were presented to that moment, we see that in active dictionary, we use to many models from the organizers of these competitions, and also Nikolai from his works, which are mostly famous for this kind of tasks. For the second, so it was for the third data set. For the second data sets, we obtained the third best results, and for the smallest data sets, we obtained the second best results. So, I mean, we still have a way to go how these results can be improved, maybe considering different cluster projections or considering more advanced transformer models for context embeddings. So overall, I would just say that as a conclusion, it's like we show that combination of contextual word representation and knowledge bases seem a promising area for further study, and the extension of BERT training data sets with word meanings from dictionaries such as glosses improved model performance for English word sense disambiguation task. And probably we believe that a similar approach can be also applied to Russian word sense induction task in a supervised manner, because in word sense disambiguation, you need it's supervised task for classification of sense, and in word sense reduction, it should be a supervised task. It's like another area of interest for us is the employment of co-occurrence graph for the Russian word sense induction task, and we have some preliminary results that will be presented today at the ICE conference. Thank you for listening for my presentation. And again, I would like to ask you if there are any questions. Welcome any questions from the audience.
Thank you very much. And I have a question about what is like the final pipeline. Where is the very good difference between your approach and ours? So can you explain this, or what your 78 or something like that is twice or several times bigger than our numbers? So why it happens?
Yeah, it's very good question. So basically, I mean, when we have this top two approaches, the data set is quite small. So I mean, in the test set, we have just 5 words with 2 or 3 sentences. So I mean, I will not be, I mean, too positive about these results because the data set is small. However, we just show that if the number of sentences is quite small, then clustering results are also better. And that's a reasonable explanations of our results, I believe, because when we have something like 8 or 7 sentences, it became much more complicated to separate the context. And in our cases, when we have just 2 or 3 clusters, then we fit quite well for them. And as for the other data sets in which we did not succeed, we also see that the other approaches did not outperform. So the maximum approach is around 30 or 45% for different data sets. So it means that the task in general is quite complex. So it means that there are too much ambiguous contexts that did not provide any kind of information to determine what kind of sense should be imbued. And maybe the answer to this should be taken from some exterior knowledge. So, for example, from built knowledge graph or from some text corpora or from some general level of knowledge, for example, on how often does this word is co-occur with some other words that are most important in the sentence or mostly related by some grammar or lexical structure. And that may be a good insight on how the results of all the models can be improved.
Oh, okay, thank you very much.
Okay, thank you very much. So I consider that's all for our session. I would like to thank the speakers and the organizers. So we have very small number of papers that are devoted to digital humanities, but in general, it's like we discuss different applications of natural language processing or either technical, I mean, more applied tasks. And in general, I would just like to inspire those who listen to the recording of our session that there are various applications in which it's not too hard to learn how to process and vectorize text representations and then build machine learning model, predictive models, and do various modeling based on natural language processing. So I inspire everybody to consider advanced conferences, dive into details about transformers and natural language understated models, and then use them in various applications. And especially it's important for developing and progressing in digital humanities, because I mean, in humanitarian sciences, it's very important to have to be able to process large number of data, and it's not possible to progress further by just reading some number of limited resources or books or something like this, because you need to go further by processing large text corpora, and it could be done only in automatic mode or semi-automatic mode with human and so on. So again, thank you for taking part, and have a good day, and you are able to continue with next sessions according to the program. See you and goodbye.
Thank you. Goodbye.
Bye.